Oh, interesting. Interesting. Simultaneously. Okay. This is a little interesting. I'll just... Okay, fine. Okay. Do not do this. Do not do this. Oh, jeez, that is... Well... That, I can already see this running incredibly slowly. Right. Wait. Okay, nobody... Okay, cool. We're going to do here, we're going to... Yeah, okay, so, yeah, all right. So I'm just gonna yield. Oh, okay. Negative. Cool. Okay. This is... Yes. Now, we're going to take everything. Oh, this doesn't actually work. Oh no. It just... So sad. Oh, this is not quite enough. What are we doing here? We're doing green. Equals 1, then no, what is this? -1 means that 0 gets ticked back to then. No, that's totally what? No. No, this is whatever, it is fine. This should not happen. This is gonna be outrageously slow, holy shit. Badge, we want badge to be a set. This is gonna be slow. Oh, Ike doing the syntax. This is not even the correct syntax. Oh no. Oh. Oh yeah. Okay. Delta. This is oh. Huh. Did I even have, I don't have this. Let's. Nice. I didn't even send you. Start cool. Start interesting. Oh, that's there's a little okay. That might be a tricky thing here. So what we want to do here? We want to. I'm gonna do that. It's like number of things you want to hit 3. Okay. If even visits and that's not. Doesn't probably work this way. And 54. Which one does it make sense? Okay, that got the right answer. So, well, I don't know. It's how confident I'm not that. It's a shot. $29. Nice, nice. All right. Let's see. I can probably explain this very quickly. So this is like not really a PFS. Well, you can sort of think of it as one if you want, but the thing with this problem is that the state space we're exploring doesn't just include our location like it often does in Advent problems, but it also includes the current time, because the current time affects where all the blizzards are. So, but because time is constant speed and like every movement takes the time by exactly 1, we can do a BFS, and like by tracking, we don't need to explicitly track the time in our state space as long as we always record it outside, and like we always like are analyzing all the movements possible from time t to time t+1. So dist, which is the the distance from the start in the BFS search space, also doubles as time in our case. And every iteration through this BFS-ish loop, we increment dist by 1. This is normal, but we also move all the winds 1 step forward. So yeah, this is some sort of hacky manual like looping code, but as before, I represent the winds as a list of pairs of vectors, where the second vector is the displacement of the wind that it travels by, and the first is its current location. And so every time through this loop, the position, the displacement is the wrong word. I would say, I guess, velocity, direction of motion stays the same. It's, spit out the same, and the position gets normally just incremented by the direction of motion. But if we detect that we hit a wall, then we can loop it around. And here, I'm not thinking too hard. I'm just like, we hit a wall when we hit a hash mark. And I did check that there are no winds in the first column that go vertically, nor in the last, so that they can't hit this location and then run off the edge of the map. So it's safe to detect looping by the hash mark. As for calculating the coordinate, well, this I put in manually, and I had a bug, but it was quickly located because I had this assertion. I guess this actually helped me, that I want to make sure that after the loop, the wind is in fact in a location that's not a wall, and that is, in the grid and all that. Okay, so that takes the list. We collect a set of all the occupied locations because we're going to query for whether a location is in the set. We want that to be fast. So that just collects it into a set. Then we go over all the positions that we know we could be at the previous time. So that's the sort of core state of the loop. This is the set of all locations that we can be at time equal to dist. This number is used later to track the number of visits to the start or end that we've done. But for part one, we sort of pretend this is a set. And, we look for, this is pre-written, but it refers to, the current location plus its 4 orthogonal neighbors for each one if it's not occupied by a wind and it is within the grid. So that's either the start or the end, or just empty space that might have been occupied by a wind at the very start, but the point is that it is not occupied by a wall and is in the grid bounds. Then that is a possible place for us to visit. And for part one, we just put that into the next set that will be used in the next iteration of the loop, and then we can set it to batch and keep looping and solve the puzzle. But in part two, the state spaces, we also track basically how many times we've visited the start and the end in alternating fashion, where the first visit to the end, you go from 0 to 1. The second visit to start, you go from 1 to 2. The third visit to the end, you go from 2 to 3, and thereby know that you've solved it. And to increment this, we just sort of have this logic here for part 2 specifically. If the current visit counter is 0 or 2, then the next place we want to visit is the end, right? We don't want to just visit the start X times and then increment the counter that way. So we track which thing we want to visit first by the parity. If the current visit counter is even, including 0, that means that the end is the next place we want to visit. So it has to be there in order to increment the visit counter. If it's odd, then we want to go back to the start. So that's how we increment the visit counter. And when visits get to 3, we can submit the answer. And this just generalizes neatly. If the problem asked us to go back and forth from the start and end multiple times, you could just change the 3 to any number, and it would eventually calculate that. That's it.